Hello everyone. So welcome back to the second week of this course on energy and climate change and the path to net zero emissions. Where we ended up last time, let us pick up from there itself. So what we were talking when we kind of ended our first week was about the carbon cycle. And what we were looking into is that the whole carbon which is getting emitted in the environment, there is a whole process which has been set up for generations, which kind of sinks carbon and which kind of maintain that balance of the carbon in the overall atmosphere. And that is where we looked into fast carbon cycle. We also looked into slow carbon cycle, and we talked about that fast carbon cycle is the one which kind of regulates the carbon on a day-to-day basis almost, and a slow carbon cycle is kind of a long-term climate regulator, and it is basically the sink which works on a long-term basis for maintaining a long-term carbon balance in the system. And that is where we also looked into that what is the present carbon cycle and what is the kind of a embedded carbon in the whole system and what is the uptake and exertion of carbon in the current cycle. That is where we kind of ended up last time. I thought of picking up from that point itself, and let us put these things in some numbers perspective before we start moving to another aspects of energy and everything. I thought of spending some more minutes on the whole thing. So let me try to explain the current situation in some kind of a number budgeting format. So if you look at the overall carbon situation, the current carbon in terms of the quantities and in terms of whatever the anthropogenic the carbon emissions, let us now look at these numbers in the right perspective. So current emissions which are there, if you look at that way, there are two major constituents of current emissions. One is we will look into this coming few slides, that fossil fuel burning and some major industries like cement and steel and all those things, they kind of majorly contributes to this current emissions, and the emissions from that is about 36 to 37 gigaton on an annual basis. Second emissions, which is a major source of emission, is land use changes. Like as the land use changes are happening, and as more and more land is getting kind of free of some of the trees, so some of the carbon which has been buried under the ground for generations is kind of coming out from those sites where some kind of ice is getting removed, and the land is getting exposed. With the exposure of that land, the more emission is happening, some through some tree removal, some forest cover being removed. So some of the buried carbon which has been buried in the ground, which all these land uses changes also is leading to increase in this carbon emission on an annual basis. So overall, if we look at that way, the carbon dioxide emission currently is about 40 to 42 gigaton on an annual basis as of now, which kind of converts into about 11 to 11.5 gigaton of carbon per year. So that is what is the emission currently, right. And now, given all the natural sinks which are available with us, the current absorption which can happen, or how much they can absorb as of now, is about almost 45 to 55% of this net emissions of today. So between 19 to 23 gigaton of carbon dioxide is what these sources can potentially absorb or sequester. Now, some of them are stored as a short term carbon and some of them are stored as a long term carbon, and I will show you this more in the coming slide. But now you can imagine almost 50% is what is being sequestered by these sources, and 50% is getting added to the whole environment on a year to year basis. So even if we start talking about a situation where the carbon addition to the environment has to stop, our emissions has to reduce to almost 50% of what they are today before we start adding further carbon to the environment. And as I mentioned earlier, since carbon is a long term molecule, for us to start reducing carbon, we have to go below 50% to start seeing any impact on reducing of the global temperature or starting of reducing the ppm level of carbon dioxide from the atmosphere. We have to go more than 50% of net emissions which are happening today. So it is a long journey which we have to travel, and I will show you in next few lectures or maybe during this course is what we will see is that our emissions are not reducing. Our emissions has been on an uptick so far, and emissions continues to be on an uptick as of now also. So it is not that though we have slowed down, but our net emissions are still on the positive trend. So while for us to start reducing this global temperature, we have to go less than 50% of our current emissions. We continue to emit more and more every year as of now. So, it is a long journey which we have to travel, and during this course we will also then tell you that what is being done, what has been the impact of that, how it has slowed down, but what needs to be done more and more to reach towards that situation where we need to reach a situation where net emissions has to be almost zero if we have to start reducing our current carbon footprint. Now, start looking into that again from a fast carbon sink and a slow carbon sink perspective. So, our fast carbon sink kind of can sequester up to 10 to 12 gigaton of carbon dioxide per year. Like what are the dominant processes is photosynthesis or respiration, both from CO2 uptake and as well as forest regrowth, as well as this I am talking about from the land side. And the offsetting process, of course, is that when the fire or drought disturbances happen, then this kind of offsets this sinking, and that emits the carbon again in the air. This is basically the cycle where photosynthesis is the prime source for this carbon sink. And of course, as you can imagine, because it depends a lot on weather condition, there is a lot of annual variability around this, because how much of rain has happened that year, grasslands available, has grass dried, are forest cover green or are forest cover dried out, how much is the snowfall that year. So, it all depends, there is a huge annual variability around this thing, but about this specific aspect, but still it is one of the major dominant factor with respect to our fast carbon sinking. Second one is, of course, as we have been talking about, the ocean carbon sink, which is a surface uptake from the ocean, and which happens through a air-sea carbon dioxide exchange and a biological intake of this carbon dioxide in the surface of the sea, right. And the issue with this, what is happening is that with global temperature increasing and with the sea temperature also increasing, this solubility is reducing. And also what is happening is that an acidification is increasing, which is again leading to a situation where this sinking of the carbon at least at the surface level also is getting impacted. So, overall, try to understand what I am trying to tell you here is that though it is responsible for 50% of the current net emissions which are happening today, but there is a variability around this which is happening because the land issue is more variable in nature. And on the sea side, this sink is slowing down because of whatever has been done to that sink over the years through all these changes which has happened over last 100 or 200 years, all these changes which has happened, because of that our sea intake has also slowed down. So, but still it represents almost all natural CO2 removal which is happening at least as of today. And why do I say that is because if we look at the slow carbon sink, which are long term sequestrations, that is a much slower process compared to the emissions which are happening today. And because see what happens is that all the sinking which is happening either through a photosynthesis process or through the biological process on the sea surface, they kind of do the major reaction, and then once reaction has happened there, the carbon dioxide from or carbon from those two sources kind of sink in and goes much below to levels which are much below the earth's surface, and kind of gets stored in form of a more permanent solution over generations. Like do you take it out in form of oil or in form of some specific stones or and stuff like that, right. So, it is happening both on the ocean as well as on the surface also. So, this whole sinking happens at a much deeper level, and as you can imagine, this takes years and years and generations for these reactions to take place, and this carbon dioxide to kind of form in some of molecule and slowly sinking to the bottom of the whole of this geological surfaces or the sea surfaces, and it goes much below there. This is a very slow process, and its rate is about 0.2 to 0.3 gigaton of CO2 per year. So, effectively, while this is a long term sinking thing, but with the fast extraction or fast generation of this carbon dioxide in the air right now, this is virtually a source which has become ineffective right now, because in terms of the magnitude, this source has become kind of a redundant source as of now because of the very high numbers in terms of the generation of carbon dioxide. While for over generations it has worked as a very good sink, right now it is becoming ineffective with the almost with so much of carbon dioxide getting emitted in the system as of now. So, on the human time scale, this has become kind of an ineffective source. So, all the sinking, if I look that way, so there is a clear mismatch which is happening between the emissions and the sink response. So, just to put these numbers again together, our current carbon dioxide emission is about 40 to 42 gigaton per year. Out of this, natural sinks are or fast natural sinks are able to like kind of emit about 19 to 23 gigaton of carbon dioxide per year, and which is primarily the fast cycle which is responsible for this. Slow cycle is not able to kind of run with these numbers. So, about 50% of net emissions today is going to atmosphere and adding to our carbon dioxide footprint on a year to year, or GHG emissions on a year to year basis. And why this imbalance persists is because I have already talked about it, that it is we do not have enough sinks available in our atmosphere to kind of absorb the amount of carbon dioxide that we are emitting yearly basis. So, IPCC, who is one of the leading bodies who is looking into all these issues right now, it says that it also gives a statement that natural sinks absorb about half of human CO2 emissions, but this absorption is neither permanent or nor scalable, because there is no way we can kind of create more natural sinks. There is no way we can kind of keep on holding on to it, because if we do tinker with our natural systems, this carbon dioxide can get emitted. It was the slow carbon dioxide sinks or a long term carbon dioxide sinks which was more permanent in nature, but that is a very slow process, and that is happening at a much slower rate at which the emissions are happening. So, that is why half of the emissions which are getting generated today goes into atmosphere and adds to the atmospheric GHG footprints, right. So, there is a very clear mismatch between the two things which is happening, and that is why we are seeing this huge change in the climate conditions these days, because all these GHGs which has been historically sequestered in the ground, historically handled much beneath the surfaces of the sea, much beneath the surfaces of the earth, has been lying there for millions and millions of years. Now, they are unable to react to the pace at which these emissions are happening, and this is leading to global warming and all those issues, right. So, this kind of tells you about what has been happening on the carbon side of story. Now, let us shift gears and let us now start looking into that while this carbon increasing, why it has been increasing, what has been the reason behind all this carbon dioxide increase for years and years that we are seeing right now. I have been talking about this industrial era, and I have been talking about what has happened over the last 200, 300 years. Let us start putting this in form of some numbers. Okay, just before we move forward, I will just give a word of caution here. Some of the numbers which I will be showing you will be on the day where I have kind of recorded these lectures, and some of the I mentioned this earlier also. So, I just want you to be aware of this fact that if you are trying to quote these numbers somewhere, please get these updated numbers on a day when you are quoting it, because the numbers keep on evolving, numbers keep on changing. So, let us now start looking into reasons of this carbon increase in a much more number based story. So, first story that we would like to understand is that how population of the world has grown over last few decades or few centuries or generations, how the populations has gone up, because remember, it is the emission per capita that finally leads and accumulates in form of a final number that we are looking at, right. So, if you look at it, we had a very low population for generations, and world was sitting at about 1 or 2 billion number of people for a very long time. And if you look at 0 AD, our population was even much in about hundreds of millions of net population at a worldwide level. It is only the advent of the industrial era from which you can see this population rising very drastically, right. If you look at the point here, the population starts rising almost at this point very drastically when the industrial era started. Life expectancy increased drastically from that point onwards. What happened was that with the advent of industrial revolution, energy was available, more and more resources were available to take care of human life. Also, there was a lot of development on the medical science, and all put together our population, our life expectancy went up drastically. And also there was a globalization which was happening, and the cross pollination of population also started happening. People started exploring new and newer land areas to go and live. With all this put together, if you see overall our population has increased in last kind of 300 years drastically from about couple of billions to about 8 billions today. About maybe we were less than a billion about 300 a year ago. Like if you just look at number at 1900, we are only 1.65 billion people on the globe. And from there to more than 8 billion people today, our growth has been phenomenal in terms of population. And remember, each person adding its footprint on the earth would mean in terms of carbon emissions, in terms of the consumption that the person will do, and in terms of resources that that person will be consuming. So it will all add up to this, and we will look into this on how to put this number in perspective more when we start looking at KANPUR-NPTEL. Before we move to energy side and how this population is expected to kind of move forward, if we look at the number right now, good news is that our population growth at a worldwide level has slowed down. Specifically, some countries which has kind of has much more matured population thing right now. The population is slowing down in those specific countries. Some part of Western world, some part of developed nation, population have slowed down. Even some countries are now showing negative growth of population also. But some part of world is still continue to grow. So overall, if you look at it, our population growth is still positive, and we are only expected to start seeing negative population growth by this late century, about 2080 or something like that, or 2090 is where we will start seeing the negative population growth. So world population will kind of is expected to saturate around that point. But the bad news is that from current about 8 billion people, we are expected to grow about 10.5 billion people before we start saturating. So our emissions per capita, even if they remain same, if we will have a footprint of about about 2.5 billion people adding up to that emissions, or about 25 to 30% more emissions coming, just if we kind of continue with the same kind of a lifestyle, and we continue with the per capita, which is per capita emissions which are similar to as of today, we will be increasing about 30% of emissions more, just in terms of number of people increasing from current about 8 billion to about 10.5 billion over next few decades. So definitely something has to be done in terms of per capita emission reduction is very clearly evident from this graph. If we have to see anywhere that we have to start slowing down in terms of net emissions that we plan to achieve. Along with that, another thing which has happened is use of our energy. So while population has been on the rising trend, along with that, what has happened is that our energy consumption also has risen drastically over the same period of time. So this graph is showing about from 1750 or 1800 what has been the net energy consumption and what has been the carbon emissions from a global perspective from the leading countries in terms of emissions and all those things. So if you look at the graph on the left, traditionally we have been a biomass kind of a consuming globe, where natural biomass, be it in form of wood or be it in form of some kind of a natural oils and all those things has been consumed. So primarily wood, it was wood and its other forms which were primarily used as sources of energy historically. Like fire was the major source of energy historically. So since fire was the major source of energy historically, and it was the biomass which was primarily being consumed, it was only with the advent of the steam engine and we learned how to use coal as a resource, which was a much more kind of a controlled use of coal, which has led to increase of consumption of coal suddenly from late 1800s or maybe early 1800s. We started suddenly resurgence of starting of coal as a source, and what coal did is that with its coal became the major source of energy generation, and along with that it came in the carbon emissions, because our carbon emissions started drastically with advent of using of coal in early 1800s. Next wave which came is with the use of oil. So next we learned how to extract oil, how to refine oil, how to use oil in our transportation system, and once we started using that, and around the same time the IC engine kind of got developed, and with the development of IC engine, with development of the technologies around that, and transportation started to move from coal based transportation to oil based transportation, use of oil went up, and with the energy density of oil looking very, very interesting, and it's a energy source which can be transported from one point to another point, we suddenly started seeing huge footprint of oil uses also, which kind of overtook coal as a major sources of carbon emission. And as you can see from this graph, oil from early 1900 it started adding to this coal footprint. Coal never slowed down, and oil kind of started going as a top layer onto it and adding to the net carbon footprint. Next wave which came is that we started to extract natural gas, and once we started to use natural gas, we further added to this energy footprint. So, see, we never slowed down in form of our energy uses. Each new source which we kind of develop, each new source kept on adding to our energy footprint. It was not that one source was being replaced by another source in a systematic manner. It was just one source was being used, coal was used, it was emitting, oil came, it started adding to the carbon footprint with the use of coal. Then natural gas came in, and we started adding to its carbon footprint, our carbon footprint even more with new sources which was being used, because world needed more and more energy, with fast development on our consumption, with fast development of humankind, with more and more energy intensive devices coming in. More and more energy was being generated, and more energy was being consumed in this whole process. One source which was getting developed in parallel, which was having much lesser carbon footprint, was hydropower, which continues to be the fourth largest energy generation source as of today also. Now things are changing of late. I will show you these numbers in coming lectures. But so the whole thing which has happened historically is that more and more sources were coming in, and everything was adding to the net carbon emissions, or in terms of the primary energy consumption by source. And it was, I will show you that how it was linking to the emission in next couple of slides. This slide is only talking about the energy consumption from that perspective. And it is only very recent phenomena that we saw some changes in energy consumption pattern, and we will look deeper into these numbers in coming lectures, right. If we just put on alongside with it on the right hand side is the net emissions of carbon dioxide. This was the energy consumption picture, and along with on the right hand side is the net emission, and I have kind of put it in form of a country wise emissions. I will show you more graphs around in terms of the source wise emissions also going along in some of the lectures. So, you will see a lot of data, but do not try to remember this data, just try to get a hang of understanding of this data from an understanding perspective. Now, if you kind of overlap these two graphs, what you will see very clearly is that while energy consumption kind of went up, the emissions at a worldwide level also started to go up, and you can have a direct correlation, almost kind of a one-to-one correlation between the graph on the left and graph on the right, where the graph on the left talks about the energy consumption by source, and graph on the right source about the carbon dioxide emissions. So, it was a very clear correlation, very strong correlation in terms of that how we started to consume more and more energy, and how did we start kind of emitting more and more. It is a very clear kind of an overlap on this. So, this graph, as I showed you on the earlier curve, that we started using more and more energy with various sources, and this is the graph which talks about emission, which is fuel wise emission. So, earlier graph that you saw was emission from a region perspective, but this particular graph is about how much emissions were happening from various sources which we were consuming. So, as you can look into it, that the coal has been historically the major source of emission. It started in 1800s, then it continued to grow, it continues to grow still. Oil came into picture around early 1900s, it has added to the footprint, gas has added to the footprint, it is other industries also which is kind of consuming, and cement, why I am mentioning specifically here is that because cement kind of do a direct emission, not only with respect to energy consumption, but with respect to its direct emission. It is scope 1 emission which kind of directly it emits during the process. That is why cement is mentioned separately. I will show you what do you mean by scope 1 and scope 2 kind of going forward, but just at this slide just try to understand that what we have is that based on the various energy sources which we started to consume, we had a very clear cut case where we started to see the emissions with respect to these sources, and which were all adding up, we kind of going along. Only we had a small dip in between when we had this COVID time frame coming in, but good part is that if you look at the slope of the curve, at least the slope of the curve has slowed down, and I will show you that what is happening on this, why this slope of the curve has kind of slowed down slightly, and what is now happening in terms of this transition on this energy sources also, and how this coal, if you look at it that way, the coal has plateaued slightly, oil has plateaued slightly. Gas still is not plateaued, but it is still kind of growing. But I will show you these numbers more deeply as we kind of go along, right. And now if you start putting these numbers together, what you will see is that net greenhouse gas emissions effectively is more than 50 billion ton. So if you remember few slides back, I was talking about 40 billion ton as carbon dioxide. That was just carbon dioxide. If we add methane to it, if we add ozone to it, if we add everything else to it, the net emissions is more than 50 billion ton on a equivalent carbon dioxide basis, and about 75 to 78% of like 40 billion ton of that is only carbon dioxide, and rest is all other greenhouse gases. So the greenhouse gas emission has been increasing continuously from early 1900s, from about 10 billion ton, and now if you remember what is our natural sink numbers. Our natural sinks numbers is about 90 to 20 billion ton carbon dioxide which it can sink. So it up to about 1960s, about 1950s, the atmosphere was able to handle the extra emissions which was taking place. But after 1960, it is kind of given up because the emissions has been higher than what the natural sinks can handle. So, and if you start correlating the increase in global temperature, you will see a very clear-cut evidence around this 1960s or 1970s that the global temperature started rising, because it is around this area that kind of sinks gave up, and they were not able to absorb the higher emissions which were taking place at this point. Now, just on the kind of matching it on the overall in terms of the number, the type of GHG. So, while this is the overall carbon dioxide equivalent which is there, as you can see on the right hand side, it is primarily carbon dioxide, which is about 80% of the net emissions which is there. Next highest is the methane, and the next highest is the nitrous oxide, and of course ozone follows just after that. So these are the major sources of GHGs which is leading to this adding of these GHGs in the environment. And as I mentioned earlier also in one of the earlier graphs, okay, maybe I did not harp upon this point. What you also see here is that not all parts of world are emitting equally. Some part of the world are emitting high, some part of the world are emitting less, and we will look deeper into these points over next lecture. But in this graph, you can see the intensity of the carbon with respect to the geography which is there, or in terms of net emissions. So high in terms of the emission, China is the country which is emitting the highest, US is the second highest emitter as of now. India is becoming kind of the third highest emitter at a global level given its number of people which are there right now, though our per capita is still much lower, but in terms of the overall number addition, we are at a third highest emitter level. So China has become the first highest one, US the second one, and India being the third largest. And there are other, as you can see, that depending upon number of people, depending upon the per capita emission of people, the emissions worldwide would be changing. We will look deeper into these numbers in terms of understanding that how the per capita is playing a role there, so how the lifestyle is playing a role over there, what is the role of population in this, and we will start looking to this number. So for now, the message from this lecture is that the carbon sink has not been able to handle the higher emissions which has happened of late. And what has happened also is that because of this higher carbon sinks which we have not been able to handle, the net emissions worldwide are increasing. And what we started looking into this lecture is that what are the reasons for these increase in this carbon emissions, which are primarily happening because of the population increase and also the consumption of fossil fuels as a major source of our energy. So it is consumption of more and more energy, and it is the type of sources which we have been using as our energy sources which has led to this increases net emissions which has happened so far. And we will start looking into these numbers much deeper into in next lecture, and then we will try to understand and make more sense out of it. Thank you.